Okay, so this simple quadratic form equal to 5. Find and plot the x-intercepts. Okay, the x-intercepts. I ask people to do this, and everybody has the intercepts. You can see how far you are along the plotting, but I don't think you'll have any trouble with that. Well, solution to x squared equals 5, which is what you get if y and 0 are both 0, is x equals plus or minus 5. So we can put that on a graph. Somebody want to put x here, y here, and z coming out. That's okay. Oh, you have the arrows in the right direction. So we have x equals square root of 5 or negative square root of 5. So this is the point. Square root of 5, 0, 0. This is the point. Negative 5 square root of 0. Square root of 5 is about 2 1/4. Okay. 9/4. All right. Over 16 is 5 and 16. Yeah. Okay. So between 2.24 and 2.25. Okay. So you can do a decimal approximation. That's fine. So far, we don't need it. We just know that whatever square root of 5 is, this distance will be the same as this one. Okay. Then the y-intercepts, well, I'll bet you're going to get so you're going to get square root of 5, negative square root of 5. Oh, we're starting to get a picture of this graph. Now, obviously, you can see the rest of it, right? Well, no, that's not obvious. Okay. What about the z-intercept? What can you tell me about the z-intercepts? Okay, so we quickly determined the x-intercepts are plus or minus 5, the y-intercepts are again plus or minus 5. The z-intercept ain't none. No z-intercept, because you're going to get x minus 0, z squared, negative z squared is 5, z squared would have to be negative 5, and there's no real solution, so there's no z-intercept, right? Okay, so as I said, well, we already know that this isn't going to be a sphere, because the sphere that goes through these points is going to go through the z-axis, right? It's not going to be an ellipsoid. Ellipsoid just like an elongated sphere, right? Or squash down, whatever, in different directions. Okay, so we don't necessarily have a real good picture of this. So let's think about what this gives us in the XY plane. The XY plane, what's the shape of the graph? Well, what's the equation in the XY plane? At least write down the equation. If you don't remember what the shape of that thing is, well, review your conic sections, but at least write down the equation. Okay. So, well, the XY plane z is 0. So the thing you could write is x squared plus y squared equals 5, right? And then, yeah, what Cole wrote that threw me off, he had a square root of 5 in there. I'm confused by the intercepts or whatever. That's what he wrote. Okay. And that's x squared plus y squared equals r squared is a circle of radius square root of 5. You don't really need to write it in this form to show what it is, but that's a good idea. Okay. Okay, so now we've got some more information. Well, we can sketch a circle of radius 5. How do we sketch a circle in 3 dimensions? Well, first we do the rectangle. Draw a line through this intercept, hopefully parallel to the x-axis to kind of screw that up. Okay, and then line through here, and then a line here, and a line here, and this helps us draw a decent circle. Because the circle has to be tangent to the square at these points. And if it's an ellipse, well, it's tangent to the rectangle. So far so good, except it kind of tapers a little bit there because I screwed one line up. Okay. Okay, well, now we're getting to start. What's it look like in the XZ plane? What's the equation? And what's the shape? Okay, so I'm not even going to look at pretty confident. You see that in the XZ plane, y is 0. Okay, now that's a conic. What's the standard form of that conic, and what is the shape? Okay, now everybody got that right when he said the XZ plane. I switch gears. I'm going to do the YZ plane first. Then I'll come back and do the XZ plane. If you did the XZ plane, it's obvious what it's going to be in the YZ plane. It's going to be y squared minus z squared equals 5. Okay. And everybody, I think pretty much had x squared minus z squared equals 5 when I asked for the XZ plane. Okay, so the YZ plane, we have this. Well, we put this into the form. Y squared minus 5 minus z squared over 5 equals 1. Well, what's the y-intercept and what's the z-intercept? Okay, there's actually no new information here except except the information is that there's a connection. Okay, what you get is you get y equals plus or minus 5, straightforward, everybody got it. You just if z is 0, that's what you get. Okay. And of course, that just mimics the points that you already have in the YZ plane. So it shows you that the circle has to intersect whatever this shape is going to be at that point, at each of those points. Okay. So there's no intercept, no YZ intercept. There's no Z intercept because, of course, as we already saw, you can't have any points in the Z axis. We already determined that. There's no Z intercept, So if you got a z-intercept here, there would be a z-intercept. Okay, so make sure everything stays consistent. All right, well. So in the YZ plane. We have there's two intercepts. All right, where do we go from here? So where we go from here is we know conic sections, we know the difference between an ellipse, a parabola, and hyperbola. Okay, if we don't, we go back and take another review. Okay, and remember what I told you on the first day. What I told you was, okay, this is y squared over a squared minus z squared over b squared equals 1. Now, you should know a lot more about conic sections than just what I'm telling you. You know about foci and, asymptotes and intercepts and all that stuff, the references, okay? But what you do is you do a rectangle, 2a by 2b. Or not 2b. Obviously, I don't know. Okay, so. Maybe I should put X's in these points because it makes them look like intercepts. Okay. So our intercepts are here. No intercepts here. Oh, that's better. Okay. So we've got this line and this line. And we got a hyperbola. All right. Come over here. That's about where I'm going. Okay, so we come over here and we can draw a hyperbola. And that's part of our graph. So yes, I've already committed to make my graph green, so I'll make these green. Now, in the XZ plane, we get the same thing. I'm not going to draw that because of the way I want to construct this one. But you would make a rectangle, actually a square in this case, with all coefficients are 1. Okay. It'd be a 2 by 2 rectangle, 2 lead points. So it'd be like this, okay, in the XZ plane. So you'd have a parabola, a hyperbola coming out like this, and then one coming in from the back, intercepting at these 2 points. Okay. We're not going to do that because we don't really need those hyperbolas. They just come up naturally. What we're going to do next. Okay, so let's see. What about in the plane z equals 2? So what's your equation in the plane z equals 2? Okay, so in the plane z equals 2, you have everybody got that. Very cool. Okay, so it's a circle of radius 3. And well, what color to use next? Okay, to distinguish this, the plane z equals 2. Well, z equals 2 at this point, right? Because we make sure I'm telling you right, at least practice something. Or was it? No, z wasn't 2 there. Z was about 2.3. Z equals 2, let's say is about here. I'm not going to label that point of z was 0, 2. And z equals 2 everywhere in a plane, horizontal plane, it passes through this point. Now, to indicate that horizontal plane, I'm going to make an auxiliary axis. I'll call it x prime. Had to bring it all the way out here so I could put an arrow on it because everything was cleared up. And here, a y prime axis. So I've got this set of prime coordinates up here, and in that, along that axis, I need to construct a circle of radius 2. Okay, now a couple of things. That circle of radius 2 has to intersect this hyperbola here, because this hyperbola is part of the graph of this function, and so is this in the x equals 2 or z equals 2 plane. Okay, so that this point here has to be 0, 3, 0. 0, 3, 2, I'm sorry. And this point over here has to be on the hyperbola. Okay. It's going to give you a circle, but the circle is going to be a little bigger than this because, of course, a couple of reasons. Hyperbola curves back here, forces that circle to be bigger. Okay. And the radius is 3, where the radius here is a square root of 5, which is about 2.3. Okay. Circle's about 25% bigger. Although if you do area, it's more like 57% bigger. Okay. But the dimensions are 25% greater, so we can do that circle. Okay, we can construct a. I'll do this kind of lightly, you know, totally mess up my picture. I'm going to use this square. That's a bigger circle. Here. I've got to come around here. Okay, can you kind of see what I've got? There's a lot of clutter in that picture, but you've got a bigger circle at a higher point. Well, no matter what number you put in for z, you're going to get another plane. And that plane is going to be such that when we plot the circle that we get, it's going to intersect a hyperbola that we drew in the xz plane. It's going to have a stack of bigger and bigger circles with hyperbolas over here, and this makes a big hole in the middle. In the xz plane, we'll have hyperbolas here because, of course, the thing is really just what we get when we rotate this hyperbola about the z-axis. And the like on the word, the thing we get when we rotate this, okay? There's a word for it in the top of my head, but, okay. Just have, okay, rotate the hyperbola, you get the figure. Bigger and bigger circles as you go up, bigger and bigger circles as you go down from the XY plane. So you can kind of visualize that. And that's called a hyperboloid of two sheets. You can visualize a hyperboloid in this case as a rotation of a single hyperbola about the z-axis. That's just unique to the fact that x squared plus y squared equals 5 is a circle. It goes 4x squared plus y squared. And what? Well, then you have an ellipse. In every one of these, you have an ellipse. You can x squared over 1/2 squared. Right? So your ellipse would be the rectangle used for the ellipse would be half as wide. Same length as the one that is here. Some of these lines, of course, end up hidden. Like this part of the hyperbola no longer be visible. So you kind of the dotted line out of it. So, okay. So on this side, you got this big hyperboloid of revolution about the y-axis. So it's going to look kind of like this. On this side, it's going to be kind of like this. And you get pictures. But you begin to get the picture from this analysis. You look at different planes, you slice this in different ways until you get a picture of what it looks like. Okay, well, that's one figure. This is called a hyperboloid of two sheets. One sheet over here, one sheet over here. And what if it was solid of revolution? Okay, but you don't really get a solid. You got a surface of revolution, right? Put the words together. Okay, what if it was this? What would be different? Take a couple of minutes, kind of think it through. You can think through where the intercepts are going to be, and think through what the shapes are going to be in the various coordinate planes. And of course, we could have done, we did the YZ plane here. The XZ plane would have looked exactly like the YZ plane. Thank you. What about this one? Okay, now I misspoke. I called this thing a hyperboloid of two sheets and even described it that way. At the same time as I was describing it as a hyperboloid of revolution. Totally different, right? So the one that I've just asked you to do is a hyperboloid of two sheets. I was kind of thinking ahead, but mostly just wasn't thinking. So what do we got here? And how does this end up giving you two sheets? Well, I'll just start out with preliminary. It's our familiar hyperboloid. So kind of badly drawn, but get the idea. Hyperboloid that opens this way. And the same in the XZ plane. So in the XZ plane. I can't draw it where I've got it, so I'll do a more careful drawing. But you get a hyperboloid this way that comes up here and opens backwards this way, and up here it opens out forward this way. That's easy to visualize. A little less easy to sketch, but it's not that hard to sketch, so we'll do that. Okay. And what happens then in the difference between this and the one we just did is in the YZ plane, you got nothing. Okay, so it doesn't intersect the YZ plane, and that separates the two hyperboloids. Okay, the two sheets of the hyperboloid. So if we try to make some sort of sketch. We got vertices here and here, also here, and here. We get those from the XY plane, these two vertices. From the XZ plane, we get these two vertices. We could label them, but I don't want to do as much labeling because I want to try to do halfway representative picture. Okay. In the really leave myself a whole lot of room here. So in the XY plane, got these asymptotes. And we've got a hyperbola that opens out here and does something similar over here, and then opens backwards here. And becomes asymptotic to this line, as well as this. So this is forward, this is backward. I have to turn in my drawing license. Doesn't look right, does it? It'll look better in a minute. I'll go to be smart. Okay. It'll be asymptotic to this. So it's going to come out with the flat and then over the line. So it'll be wider. Okay. It's going to be flexion, I guess. In the XZ plane, you get the same thing. So we can draw a line here, and then here. So we've got our rectangles and copies. Not exactly behaving the way I want it to. Made it too narrow, but we're going to use it anyway. And then we're going to have our asymptote here and here with intercepts here and here. Where's my asymptote? I can't find it. Here. Here. Best one. So anyhow, it's going to be kind of like this in the XZ plane. So that what you have is surface of revolution here and a surface of revolution back here. And I'm not going to take and complete the drawing because I misplaced this one. Rectangle should have gone over this way. I didn't really leave myself room to draw it. In any XZ plane, let's look at what this looks like. Here's the plane. Z equals 2 again. Then we get okay, so we can come up here and draw a bigger rectangle. We're going to need a bigger rectangle because the hyperbolas are receding this way and coming out this way. But we're going to be able to draw those. Okay. So we look at the pictures. I'm sorry, I messed up that construction. We'll try another one. Okay. Ellipsoids are really easy. Maybe I need to do something easy. I'll point out that if we put coefficients in front of X, Y, and Z, that just distorts things, stretches it this way in the X direction or compresses it, stretches or compresses it in the Y direction, stretches or compresses it in the Z direction. So that this hyperboloid of two sheets can get skinnier this way and fatter this way. Okay. Yeah, one other thing about it. Within the wrong things. What do we get in the plane X equals 4? The plane X equals 4, we're going to get 4 squared is 16. We're going to subtract 16 from both sides to get negative 11. It's the same as y squared plus z squared equals 11. That's approximately it's approximately this, it's a circle. If I had different numbers in front of y and z, it'd be an ellipse. Meaning, I'm going to go with the plane x equals minus 4, which is something that it's squaring x. So if we look back here and slice this, okay, this point back here is only at about 2.3 units, okay? Actually, the negative 4 is back here, so we slice this section of the paraboloid, the hyperboloid, with a plane, and we get a circle. In general, we'll get an ellipse if we have different numbers in front of y and z. Not hard to visualize, right? So if we go back to the x equals negative 4 plane, within this plane, we slice the thing and we get this circle. Add the drawn circle. A little hard to see what it means unless you already know what it means. But if you look at a good picture, you see how that works. Okay, so in any cross section, assuming we don't have rotation, then we get rotation if we got X, Y's or Y, Z's or X, Z's. If the thing isn't rotated, then in any plane parallel to any coordinate axis, you're going to get a conic section. Okay. So slice it anywhere like this, what do you get? Slice it anywhere like this. You're going to get some kind of conic section, and you can always write out the equation. Because any of those planes will be x equals some constant, y equals some constant, z equals some constant. Okay. Okay, so we're going to do an ellipsoid. I'm going to put some numbers in front of these. Let's say we've got okay. What do you get in the XY plane? What do you get in the XZ plane? What do you get in the YZ plane? Okay. So, well, I've written it out in the XZ plane. If you divide both sides by 36, of course, you get x squared over 3 squared plus y squared over 2 squared plus z squared over 6 squared, right? So I could write that out as now, whichever one of these you set equal to 0, you're going to get an ellipse. Okay, so there you have it in the XY plane, the XZ plane. And the usual orientation for the XZ plane, the Z plane is like this. The axis is like this, the X axis is like this. It's going to be, leave myself much room there. I need more room in the Z direction. Going to be still not really to the same scale this one is, but Z is going to be up at like 6 here, -6 here, 3 here, -3 here. And drawing parallel. There we've got it, and here's our vertical ellipse in the XZ plane. That's in this plane. Then in the YZ plane, without actually drawing it, it's going to be even more elongated. Go from 6 here down to -6 here, only out here, -2 here. Going to be a long studio bench. Okay. Draw that in 3 dimensions. I can start out with the ellipse in the XY plane, which is just this one. It's -3 here, -3 here, 2 here, -2 here. And you get if you go higher, like let's say to the X equals 2 plane. I'm sorry, the Z equals 4 plane. Okay, so we go up to Z equals 4. Might be up there. In the Z equals 4 plane, you got 4x squared plus 9y squared equals 20. Instead of 36, because Z squared would be 16. I chose the Z plane because first place, we want to think maybe stacking these things vertically. In second place, I don't have a 4 in the mind to worry about when I do the arithmetic. And you don't need, it's more obvious. So we get x squared over 5. Then it's going to be y squared over about 2.2, which is about I'm just going to do approximation, call this 2.3 squared, 1.1 squared. We do the exact figures, you know how to do that. And then what we have up here then in this plane they confuse it with colors again. We do an auxiliary x-axis and an auxiliary y-axis. And we only come out 2.3 on the x-axis, whereas we came out 3 here. So the point directly above this one, we come in a little bit. Point directly above this one, we come in a little bit. The point directly above this one, why do we come in? That way, that's not. Now we're going to come in here. We're going to come in here. Then we're going to end up with a smaller lift. And we go up to the plane Z equals 6. And all we got to the point. The Z equals 6. Z squared is already 36. We can't add anything to that. And these don't allow us to subtract. Okay. So we come up to the plane with Z equals 6. That's as far as we're going to go. Okay, so now at this stage, we can try to sketch a curve on our surface. It comes in like this. It's up here. And it's done at this point. Now this point corresponds to this point in the XZ plane, right? And I don't know if you can see it. I've got 6 written here. Okay, that's Z equals 6. So we're actually drawing this left. And if we do that, it's going to come around like so. Then down through this point, and down to here. And then it'll reflect down underneath. Same way. So we're beginning to get a picture. Okay. And we can complete that picture by sketching it in the YZ plane. Looks like this, comes up to 6 and over to 2. Well, comes up to 6 at 0, 0, 6, comes over to 2 here. Let's label this point, make sure. So we're starting to get kind of a wireframe diagram. although some of these lines are hidden and some aren't. And well, if we come out in this direction, let's just shade a couple more lines. And eventually, something that starts to look like an ellipse is going to emerge. And we draw some circles. So following the shape of this circle, and at least starts to suggest an ellipsoid. Now, what's happened by putting okay, if it was x squared plus y squared plus z squared equals 36, we'd have a whole sphere of radius 6. All the way from up here, all the way to down here. By putting a 9 in front of y squared, we've shrunk that down to where its width is only, well, it's a sphere of radius 6, its diameter is 12, right? Putting a 9 here, we've shrunk that 12 down to 1/3 of that. It's like we've replaced y by 3y. Remember recalculus? Replace y by 3y, you stretch things, okay? In this case, you compress it by this much, okay? Actually, if you replace y by 3y, you compress it by factor 3. Okay, so we compressed this by factor 3, just like you would in pre-calculus. In the x direction, we've compressed it by a factor of 2, from a radius of 6 to a radius of 3, diameter of 12 to diameter of 6, by replacing x by 2x. In other words, if we had right. So you can see this as the sphere compressed by factor 2, 3 this way, and factor of 2 this way, and no compression in the z direction. We just see that as a squashed up sphere, squashed different ways in different directions. And of course, what if you cut this with the line x equals y, or the plane x equals y? Okay. Because all the points where x equals y, well, down in the coordinate plane, they make 45-degree angles with the x and y axis. But you have any z. If you say x equals y, you haven't restricted z. So you have a plane. So now you've got this squashed up cone cut this way. What's the equation? Well, if x equals y, you could either replace x by y or y by x. What you get is then this, which is 13x squared plus z squared equals 36, or x squared, 13 over 36 is about 1/3, which is a square root of about that. So, and there's something wrong with that. It's about 3. Makes it too skinny. I should have 36 over 13, which is 3. Anyhow, use an equation. It gives you the equation of the ellipse as it would be in this plane. For some reason, it seems like it's coming too close to the origin. Anyhow, that's what you can do. Something else what I do. Not going to take time to fix it. Get the idea? Okay. Later on, we talk about intersecting. This is visible. So okay, that was better. Talk about intersecting this visual plane. Done equations of planes, right? We can take a plane through this point with normal vector slices, and what do you get? And so we've got an ellipse. Got a cone, you get an ellipse. Got an ellipse. Ellipsoid, you get an ellipse. Kind of seems like it would. And maybe it's an ellipse that's rotating a little bit. Maybe it's not even an ellipse. Okay. You could take the equation of that plane, which is an ax squared plus bx squared plus cx squared equals some number. Okay. And eliminate variables and get the equation of that figure. We'll do that later. I just want you to see geometrically. You could be intersecting these things. You could intersect this thing with a smaller sphere. What would that intersection look like? Try to visualize it. Okay. The algebra can get a little bit trickier. Not too good. Okay, well, that's the idea of quadratic surfaces. You can have ellipsoids, you can have hyperboloids in one sheet, hyperboloids in another 2 sheets. You can have paraboloids. You didn't do paraboloids, they're easy. You don't like. If one of these isn't squared, then that gives you a parabola in one of the coordinate planes. Okay. Or you could even have a paraboloid of revolution, an elliptical paraboloid. You understand what you get out of this, then those other details become easier. The whole idea is look at what happens in the coordinate planes. Then think maybe of z equals 2, z equals 3. What happens in those planes? How does it stack? Or x equals 5 or y equals 2. So you can get a better visualization. I don't think WebAssign does a whole lot with cutting the planes with anything but the coordinate planes. Right? They don't ask you to construct anything, but y'all look pretty good with construction. Okay, so make sure you do some of that. Draw these things by hand. Make sure you understand how the pictures come about.